We have already seen the algorithm merge, which merges two lists that are already sorted, and it does this in linear time. So now we're going to illustrate how a recursive programming algorithm works. And this is the merge sort algorithm that I'm going to illustrate. So the lines of code are usually quite simple in recursive programming. They're very short, but the number of evaluations of the basic functions can become quite complicated for analysis. So we call it recursive because it calls itself. The algorithm merge sort has arguments. A is an array, P is the left index of the array, and R is the right index. So for example, here it would be 1, 2, 3, 4, 5, 6, 7, 8. So P would be 1 and R would be 8. Then the algorithm, what it does when we call this type of algorithms divide and conquer algorithms, is because they try to do the job in smaller sizes. So what this does is calculate the midpoint. In this case, because there are 8, the midpoint would be leaving 4 on one side and 4 on the other. So that's the midpoint of that array. And then it calls the same function. So it is a call to the same function, and that's the recursive part of it. It calls the function for the left array from P to Q, say from 1 to 4, and it calls it for the right array, say from 5 to 8. And then it calls the merging of those two. So if these are sorted, then we have to merge them. So I'm going to illustrate how the algorithm actually looks like, how the compiler would do it in using an analogy. So the analogy that I'm going to use is that I want to solve this problem, but I don't know how to solve it. It's too complicated. So then I have a friend, Sam, and Sam is telling me that she can solve it, but she can solve only smaller ones. So she is gonna do half and half, so that's the divide part. So she's gonna do 4 on one side, 4 on the other, and then of course she's gonna be using the merge algorithm to deliver. So she says, yes, I can do it, I can do it. But she really doesn't know how to do it. She says, if I could just sort these two piles, it would be, then I can do the merge. Merge, I understand. So she says, but how do I do this? So here comes Alex. Alex says, yeah, no, I can help you because I can do it in smaller parts. So I'll do it in groups of 2. So Alex has to do 4 times the job. And he says, yes, I can deliver, because then he can do the merging really easy, and then he can deliver. So the promise that he has to Sam is that he will deliver 2 already ordered lists, and then of course he can merge them, and then she can give me the final job. But of course, as you probably have already guessed, Alex doesn't know. So another subcontracting. Alex says to Paul, I need to do this. And Paul says, yes, I can do that. So Paul considers each one of the cards, and this is of course where the middle point in groups of 2 is just considering groups of 1 at a time. So for groups of 1, they're already sorted. And because they're already sorted, then Paul says, I'm ready to deliver to Alex. I promised Alex that I was going to deliver pairs that are ordered. So now Paul uses the merge algorithm that says you take the top card on each of the piles and you put the smaller one in the left and the other one on the right. And so this is already ordered. So he's already ordering. So this one goes like that. And that one is already ordered. So he delivers to Alex what he promised, which was 4 lists, but already ordered numbers. So Alex says, oh, now I know how to do that, because now I only just need to use the algorithm for merging these cards. And the algorithm for merging, which we have discussed already, is in merging these two, just take the top one and you compare. So you put the smaller one on the left, and then followed by the next one, followed by the next one, and the next one. That's sorted. And for this pile, he again looks at the sorted lists or piles, and so he puts them in order. So this is the first one that comes, then comes that one, then comes that one, and then comes that one. So Sam is almost done. Sam says, okay, now I can pay Alex and everything's fine, but now I need to deliver the final answer. And the final answer, of course, is to merge these piles. And merging these piles, that is done again, remember, in linear time. So the final answer is just to pick the smaller of the top cards on each of the piles as they are discovered. And so that way, Sam finally gets the array, the original array, completely sorted. And so now she can present me with a bill. So what you need to think is, if each person is going to be charging for the work that they're doing, how much work was done with this algorithm? And that's the analysis of complexity. And of course, what I've done as well is that I've tried to introduce already a technique which is called the recursion trees, which is a way to visualize recursive algorithms that can help us evaluate as well the running time of the algorithm.